The work I'm presenting today is a collaboration with my colleagues, Doug Brinkerhoff, Martin Trufer, and Tim Bartholomew. And when Davey asked me for a title for my talk, I quickly, maybe too quickly, replied, "Projecting Sea Level Rise from the Ice Sheets, the Good, the Bad, and the Ugly." Well, now in hindsight, I don't think it was that, well, it was such a good choice, and I'm thus only going to loosely stick to the theme. I also want to point out that the names here and the pictures below are in purely random order. That does not mean Martin is the ugly one, the bad one, or Tim the ugly one. Just to get that out of the way. I hope during this talk I'll be able to convince you that the ice sheet modeling as a field has come a long way since the early days. And also that a lot of the progress in glaciology has been and still is being community driven. For example, Exhibit A here, this IGS seminar series. However, we are also not where we want to be in terms of making credible projections of ice sheet mass loss. While we've moved quite a bit closer to this goal, we are just not there yet. And lastly, even the best community effort can only bring us so far. It can only bring us to a certain point if we don't have sufficient funding available. So how does this talk come about? The story starts, I think, sometime in March 2020, just after the first order draft of AR6 had come out. One morning, I found an email from Tim in my inbox. I think it had the subject line, "Seen the draft of IPCC AR6, question mark." That was the beginning of a long email thread between me and Tim, and it's later got extended to Martin and Doug. What had piqued our interest is this figure, or the draft of figure 917, it showing the historical and projected mass loss from the Greenland ice sheet. The observational reconstruction of INBI is plotted along with model simulations. As you can see, in 2015, there is a break in slope, and I've tried to highlight that with the inset. I'm afraid the quality is a bit poor. So there's a break in slope between the historical observations and the model projections. So observed contemporary mass loss appears to be much larger than simulated by the models. So we started wondering what that actually would mean and why that's the case. Wouldn't it be likely that underestimating present-day mass loss would translate to underestimating future mass loss? After over 1.5 years going back and forth, exchanging ideas, doing some analysis, discussing things, we finally ended up summing up all of our thoughts in a commentary that came out in the Cryosphere at the end of last year. So that figure to me raises some questions. First, what is actually going on? But also, how did we get here? And I think most importantly, how can we move forward? What can we do about it? Before we delve into figuring out what's going on, let us put things into perspective. I think it's tempting to dwell on this figure too much without considering the bigger picture. So let's first address the question of how we got here. Compared to climate modeling, ice sheet modeling is a much younger and also a much smaller discipline. In the next couple of slides, I'd like to highlight how far we have come in the last 30 years, from the first thermomechanically coupled ice sheet models with only crude initial and boundary conditions to today's sophisticated models that are driven by high resolution boundary conditions. In the early 1990s, the first thermomechanically coupled ice sheet models were developed by pioneers like Catherine Ritz, Philip Huybrechts, Ralph Greve, and several others. One of my favorite figures from this area is actually from Ralph Greve's PhD thesis. I can't remember whether that made it into a publication or not. And in case you don't speak German, that actually might be a good reason to learn it. On the left side, you see a contour plot that shows the subglacial topography as it was known back then. And on the right side is a plot of an early simulation with Ralph's Psychopolis. I think a few things are worth noting. First, back in the 1990s, when those simulations were made, we only had a crude picture of the topography between Greenland. And we also didn't have this detailed view from space that we have today. At that time, I think we can say glaciology was kind of data poor. It almost didn't matter how sophisticated the models were. It, in my opinion, basically boiled down that you kind of get garbage in, garbage out. Second, and on a more positive note, things are much better than they appear. You know, if you compare the two plots, even though they're hard to compare, one is a vector plot in grayscale and one is a nice color figure, they're actually much closer. The simulation does capture the main flow directions well, transporting ice from the interior accumulation area to the coast. After a couple of years in 2001, we get to IPCC's AR3. I tried to download the old report the other day and look through it, and actually, as far as I can tell, I think only one ice sheet model was used for AR3, but someone may know better, so please feel free to correct me. Two things I'm highlighting here. First, the report states that the Antarctic ice sheet is likely to gain mass, and however, loss of rounded ice leading to substantial sea level rise from the West Antarctic ice sheet is now widely agreed to be very unlikely during the 21st century. I think the scientific consensus on these two statements has evolved quite a bit since then. Six years later, in 2007, the Ford assessment report came out. AR4 did not include any ice sheet model-based projections because of that famous line saying that at that time, models are not able to track observed changes in Greenland and Antarctica. So why was that? Why didn't IPCC trust the models? I'm trying to illustrate this here with the figure on the left. If we took all the data that we had available in 2007 and fed it into an ice sheet model from 2007, I think the result would roughly look something like the figure here. So on the left-hand side, you see observed surface speeds given in meters per year. Blue colors and red colors indicate fast flow. The fast flow is, as we know, concentrated near the coast. The model on the right side, however, it does not show blue and red colors. Fast flow is more or less missing. So this poor performance of the model and the exclusion from IPGC led to quite a frenzied model development. Each modeling group tried to up their game, focusing mainly on implementing approximations to the conservation of momentum equations. So AR4 asserted that the main reason for the model's failure to reproduce observations was the lack of solving the Stokes equations, and instead the model were using simple approximations thereof. I think as a result of that statement, ice sheet modelers around the globe started developing Stokes and higher order models. As far as I remember, one of the first Greenland-wide Stokes simulations was made by Fabien Gilles-Cholet in around 2012 using Elmer ice, but the ISSM had gained similar capabilities around that time too. Along with Stokes models came advanced data simulation capabilities. This figure here is taken from a paper by Mathieu Morlighem in 2010. It's on the spatial patterns of basal drag beneath Pine Island Glacier. And it shows a comparison of an inversion for a shallow shelf approximation, a higher order model, and a Stokes model. If that rings a bell, we can, of course, trace that back to inversion methods in glaciology and Doug McGill's seminal paper on the use of control methods in ice sheet modeling that came out in 1993. Related to data assimilation, sensitivity analysis and uncertainty quantification methods also found their way into ice sheet modeling. Here's an example from a paper by Eric Laroure and others who evaluated error margins of mass flux across Pine Island Glacier, given currently known error margins on ice thickness, basal friction, and ice hardness. Now, I could go on and on. There have been so many modeling improvements that I can't list them in 1 hour here. So if your favorite model development has not been shown, I apologize. Please blame it on the lack of time. Now, all these modeling efforts were greatly facilitated by the availability of new observations. Be it time series of mass change as measured by GRACE or near complete surface velocity fields derived from SAR satellites, or all the measurements done by NASA's Operation Icebridge. This is great. So we were finally, but slowly transitioning from a data poor to a data rich field. So again, let's move a few years forward to 2013 when IPGC AR5 came out. Are the models now up to the task? Well, with better observations and better models at hand, a group of modelers formed the sea level response to ice sheet evolution or sea rise community effort. I think it was started by Bob Binchadler, and later Sophie Nowicki took a big stake in that too. For the first time, modelers performed a standardized set of experiments that were actually aimed at estimating mass loss from ice sheets. But if you actually go into the fifth assessment report, it's kind of disappointing. We will find the sea rise effort only mentioned in passing, along with another study that used the flow line model for Greenland. So unfortunately, again, models were deemed just not up to the task. So we can do the same exercise again. This time we use data and a model representative of 2013. As you can see, the results remain more or less the same. The models are still not able to capture fast flow in Greenland's coastal areas. Well, at least not without inversion. So what's missing? In my opinion, 2014 was a real watershed moment for the modeling of the Greenland ice sheet. While the models kept getting better and better, it wasn't model improvements that did the main trick. I think it was a $100 million investment by NASA. Operation Icebridge under Tom Wagner spent 10 years mapping ice thickness across Greenland, particularly in coastal areas. And I don't have to tell you that glaciers generally flow downhill, and ice thickness exerts a first order control on ice flow. So if you don't have accurate ice thickness, you just can't accurately reproduce ice flow. So we're back to what I mentioned in the beginning. If you put garbage into the models, well, you get garbage out. But finally, when Mathieu released the first version of Bad Machine in 2014, that has made a big improvement. It's not all perfect, but at least the bigger picture has changed. Models are now able to reproduce most of the fast flow in coastal areas. So finally, that brings us back to today and the sixth assessment report. For AR6, we now finally have a multi-model ensemble thanks to the ice sheet model intercomparison for CMIP6, which was led by Sophie Nowicki and a couple colleagues. Along with other community efforts, IPGC decided that now it was time to use model-based projections of ISMIP6 in their report. So, is it all rainbows and unicorns now? It's not, and I've already alluded to that with the title of the talk and the early slides. So let's go back to that figure with the break in the slope. To better understand what is going on, we downloaded the ISMIP6 archive for both Greenland and Antarctica. But let's start with Greenland. I think for Greenland, a clear picture emerges. The ISMIP6 simulations systematically underestimate mass loss or underestimate relative cumulative mass loss when we compare them to observations, here provided by IMBY. Indeed, it is the 95th percentile of the IFSMIC 6 experiments that follows the observational record of mass loss. And this implies that either model uncertainty is underestimated, the ensemble is a biased predictor of cumulative mass change, or it could be both. For Antarctica, the picture is substantially different, with the spread in simulation much larger than observational uncertainty. In this case, many simulations that are not consistent with observations yield a predictive variance that is also not reliable, albeit this time in the direction of too little specificity. That our models are still having a rough time reproducing observations. I don't think that's a surprise to any modeler out here. We do know our models best, and we know their shortcomings. So the real question here is, what can we do about it? In the next part, I'd like to make a few suggestions that our little group has come up with. But before we go there, yes, you can reproduce these figures and confirm it yourself. It's all in the binder notebook, and the link can be found in our paper, or I'd be happy to share it after the talk. So let's come up with a path forward. To make accurate predictions of the cryosphere's contribution to sea level, it requires that models fully characterize uncertainties in model structure, parameters, initial conditions, and boundary conditions. But also the models should yield simulations that actually fit observations within observational uncertainty. If the first point is not satisfied, then predictive uncertainties are likely to be underestimated. If the second condition is not satisfied, then the distribution of model predictions is likely to be biased relative to reality. So these two suggestions, of course, these are not new ideas. And no, I don't think we will ever be able to account for all sources of uncertainty perfectly. Nonetheless, we should try to account for as many as we can. I think here is where framing the problem in Bayesian terms could come in handy. And now, whether you want to consider Bayesian statistics as the good, the bad, or the ugly, I'll leave that up to you. I am not going to dive very deep into Bayesian statistics here and spend the rest of the talk just showing equations. First, I don't think a detailed treatment would help much to get the message across. And second, I'm by no means an expert. All the formalism that is presented in our paper was developed by Dr. Brinkerhoff, so he gets the credit for that. The first we have to tackle is model uncertainty. Model uncertainty is sometimes called structural uncertainty, and it comes from the lack of knowledge of the underlying physics in the problem. It depends on how accurately a model describes a true system for a real situation. And considering the fact that models are almost always only an approximation of reality. And this, of course, is where ISMIP6 and other efforts really shine. They are a means to assess uncertainties coming from models, because we use an ensemble of different models that ideally have different physics, different implementation, different numerical approximations, and so on. So this is really where efforts like ISMIP6 shine. Now, initial state uncertainty, that remains a tough cookie. I've always liked the analogy. I think I first came across in a paper by Vaughan and Arden. And the idea is that century scale ice sheet predictions are similar to short-term weather forecasts, because both depend strongly, or at least depend on the initial state. But here's a complication. We know from stability analysis that weather predictions, we can do them up to like 7 to 10 days, and then they become poor. But we actually, as far as I can tell, we don't know that relevant time scale if we want to do ice sheet forecasts. So we don't know whether after 100 years that should be considered ice sheet weather or ice sheet climate. Furthermore, if we want to do some stability analysis and run ensemble ice sheet forecasts, we need to do a perturbation analysis. And which variable should we actually use? A couple of years ago, I remember at the conference, I think in Montreal, Mathieu, Doug, and I had a chat over lunch and did a little bit of brainstorming, and we came up that we should try doing a perturbation on ice thickness. That would make a good candidate. But I'm still kind of fuzzy on the details, how I would actually go about it. Many physical processes remain incompletely understood, or they are difficult to implement in a model. We thus have to use parametrizations of these processes. And parametric uncertainty arises because we are frequently unable to accurately prescribe numerical values for the parameters in our parametrizations. Fortunately, we can address parametric uncertainty using Monte Carlo simulation. This is conceptually easy, but it's also computationally quite challenging. Of course, it has been done in the past. Examples for studies that investigated parametric uncertainties include Stone et al. In 2010, up to more recent papers by Hill et al. In 2020, and a lot of papers in between. So large ensembles to study parametric uncertainties are now pretty standard. I think the days are gone where you can submit a paper with one single simulation with one fixed ice flow factor. And that's a good thing. So what's beyond ISMIP6? At the moment, we have predictions of sea level contribution that, in our view, are too certain and are most likely biased. I'm illustrating this here with just a simple normal distribution. So that's our starting point. A future effort, let's call it ISMIP6 for simplicity, should build on all the things that made ISMIP6 successful, in particular, the exploration of model uncertainty. Ideally, for ISMIP 7, modelers would also perform parametric uncertainties or studies of parametric uncertainty and use randomized realizations of climate and ocean forcing. What we would expect to happen from such an effort is that the resulting sea level distribution actually gets wider, meaning that we are less certain about our predictions. This is a feature of the proposed approach and not a bug. However, I think we need to do more and we can do more. We also need to condition our simulations on observations. You'll see this called Basin Calibration or sometimes importance sampling. We start with an uncalibrated ensemble of simulations and the corresponding probability distribution, which is called the prior. Then we weigh ensemble members based on their likelihood relative to observations. We resample simulations proportionally to these likelihoods to create a new ensemble that is now consistent with respect to observations. And that resulting distribution is called the posterior distribution. Also, that's not a brand new idea. There are several recent examples in the literature, in particular work by Isabel Nias and Guilford et al. In 2019 and 2020 respectively. One question that comes up is, which observations should we use for calibration? We think that a natural choice is actually the quantity of interest. And in our case, we want to predict mass loss, so we use mass change. Another good target, if you haven't done that already, are surface speeds or surface velocities, because previous studies have shown, at least for the next 100 years, that uncertainties in ice flow parameters contribute significantly to uncertainties in future mass loss. So let's put this together. We started off with ISMIP 6. That's the blue distribution. It appears to be pretty certain, it's pretty narrow. And then we go on and we add more better uncertainty for quantification in a future project. So we would expect this to be wider and maybe have a slightly different mean. So this is ISMIP 6 here, the orange curve. But finally, after conditioning on observations, we will hopefully arrive at a more credible estimate of the future contribution of ice sheets to sea level. So we reduce the bias, and because we condition it on observations, the spread gets narrower. I'd like to give you an idea of, or I'd like to give you an idea that this kind of calibration actually works. So I'm showing you here a plot from a manuscript that Doug and I are going to submit sometime later today, hopefully. For this, we performed the two-step calibration. First, we calibrated ice flow parameters, and then in a second step, we used importance sampling to weed out ensemble members that showed poor agreement with cumulative mass loss from INBI. On the left-hand side, you see the historical mass loss, the cumulative historical mass loss from 2010 to 2020 from INBI. The solid line is the solid vertical line is the mean, and the two dashed lines indicate 2 sigma standard deviation. The uncalibrated ensemble is called the prior. The median of the prior for all three RCP scenarios overestimates the mean mass loss. And the distributions are pretty wide. However, even after the first step of calibration, that is calibrating ice flow parameters, we already arrive at a posterior which shows much better agreement with INBI. And finally, if we move to the fully calibrated ensemble, that is, we calibrate ice flow parameters and then we condition on mass loss. Now we got excellent agreement with INBI, which of course is by design. On the right-hand side, you see the corresponding distributions at year 2100. So in both cases, or in all three cases for RCP scenarios, 2.6, 4.5, and 8.5, both the bias and the spread are greatly reduced compared to the prior ensemble. What we are proposing here is not going to be easy. To make it really, really happen, what we think we need is a massive international and interagency effort in both model development and also in long-term observational capabilities. We also need more professional support and access to high-performance computing resources. As far as I remember, an informal poll during ISMIP 6 came up with that modelers were willing to do a certain amount of simulations, but at some point they would love to do more, but basically they don't have funding for it and there is not enough HPC resources available for free to actually do all the simulations that the modelers wanted to do. So that's where it kind of gets ugly, in my opinion, because given what it is at stake, projecting sea level is an effort that is just severely underfunded. As far as I recall, ISMIP 6 and other efforts were pure community efforts that received very little direct funding. In that sense, it's actually quite amazing how much we were able to do with so little. My colleague Ginny Catania estimated that the annual budget for glaciology of the National Science Foundation. For my non-US based colleagues, the NSF is the main funding body in the US for our projects. Yes, NASA has funding for cryosphere as well. But Ginny estimated that NSF has about $5 million per year available for glaciology. And that's for glaciology, that's not just for sea level predictions. And that's peanuts compared to the budget of just an average blockbuster movie. For example, according to Wikipedia, the budget for Spider-Man No Way Home was about $200 million. So let that sink in for a moment. I'd like to end where I started. I think it's great to have such an engaged glaciological community, be it through IGS, efforts like INBI, ISMIP 6, ABU-MIP, ISMIP Home, LARMIP, you name it. And through those community efforts, ice sheet modeling has come quite a long way. However, we are not yet there. It will take a lot of effort and additional funding to come up with predictions that we can genuinely call credible. And with that, I would like to end my talk. It's always good to remind everybody that all models are wrong, but some are useful. And that's a quote from George Box, a famous statistician. So I thank you for your patience. Thank you.
Thank you so much, Andy. As usual, if people have questions or observations or comments, please pop them onto the chat, and we can get you to unmute and ask a question. Lev, do you want to make your point? That was put quite early on the chat, so I wasn't sure whether it was still pertinent, but Lev, you're first if you would like to go first.
Okay, well, I just always found it a bit ironic in terms of that 2007 statement when, if you look at what the climate models were doing, you know, precipitation fields or even temperature fields on regional scales are pretty pathetic back then too. And there's still a lot of divergence between models. So it's not just the ice sheet models. But I'll make one other maybe more relevant, more recent point. I just want to, in terms of what Andy was talking about, part I'd really emphasize is the uncertainty assessment, because with Bayes' theorem, if your likelihood is misspecified, your posterior is meaningless, basically. It can be very sensitive to the specification of the likelihood, which is where the uncertainty assessment occurs, because it's basically saying how does your model output compare to the data, to your constraints, given the uncertainties in the system. And it's not just observational uncertainties, it's all the modeling uncertainties. So there's actually a discussion paper in CP on that topic, but it's kind of long and it's been a challenge to get reviewers for it. But if people are interested in how you can actually go about detailed model uncertainty assessment, it's kind of laid out there in a number of pages.
Yeah, I completely agree with you, Lev, and especially in that kind of across models uncertainty quantification that I think we have to do, things will get really messy and tricky. And it might just take quite a while to figure out how we can do it. And again, like, I don't think we're ever gonna do it perfectly, but that shouldn't stop us to at least start. And I'm glad to hear that there are now more and more papers in discussion are coming out that address that challenging topic. And just to your first point about climate models, that's true. I basically ignored that here. I just assumed the boundary conditions are given and they are external. And I didn't want to discuss or put the blame too much on all the ice sheet models are perfect, but just our boundary conditions are, are wrong. It would take a whole other 10 lectures to discuss all the issues that we have with previous and even with the current state of CMIP6 models. I completely agree with you. It looks like Doc has a question.
Yeah, Doug, go ahead.
Yes, Andy, that was a fantastic talk. Thank you very much. And I want to lead off by just saying that I confess that The Good, the Bad, and the Ugly is one of my favorite movies, far better than Spider-Man. My question is about something I know personally nothing about, but I've heard the term model emulator used in the context of some Earth system modeling problems and things like that. Do you know anything about model emulation, and do you know if it's being tried in the glaciological community or that sort of thing? Just off the top of your head. Thank you.
Thanks, Doc, for that question. I can try to answer. Maybe Doc Brinkerhoff, if he's still around, may want to chime in and call me out if I say something wrong. But actually, emulators have been used in the glaciological community in a number of papers and in a number of ways. One is I think one of Doc's papers where an emulator has been built to emulate an ice sheet model, but not a whole ice sheet model, but just the way to go from ice flow parameters to surface velocities. So that's all it does. And what it can help us with is providing a means to estimate parameter distributions that yield good agreement with surface velocity observations. And I think this is a good way of using an emulator, because what it doesn't do is using an emulator to emulate a complex physical process. So the emulator is not being used to make the actual predictions. And I think that's quite an advantage. I would be a bit more wary of trying to directly emulate models that try to make predictions. But I am not at the forefront of that field. So maybe what I'm saying right now is already outdated and has been done, and maybe it even should be done.
Thank you.
And there are other papers, I think, from Frank Patton's group, and I forgot the names. Yeah, exactly, Frank, thanks. Poultice et al. Used an emulator in 2019, and Tamsin Edwards has used emulators in a couple of her papers, I think in a slightly different way, if I remember correctly.
just shorter description of emulators. I've been using them for almost 20 years. You should just think of them as generalized nonlinear regressors. It's basically just black box nonlinear regression, so you can do large sampling with Markov chain Monte Carlo or whatever. It's an easy way to think of them.
Okay, thank you. Daniel.
Hey, fantastic talk. I just wanted to ask, do you think Operation Icebridge is kind of drawn to a close too early?
I wish it would go on, and I also wish there would be a similar effort in Antarctica to fly around the coast. And while Operation Icebridge in Greenland has focused on the coast and has resulted in a greatly improved understanding of subglacial topography in that area, the interior is still pretty blank if you look at the flight lines. So I don't know where I would put the error bounds on the number of how much ice there is in Antarctica. The same is true for Greenland. We understand the changes much better, and we can measure them way more accurately than we actually know the absolute numbers. So in that sense, yes, I actually wish there would be a continuation of Operation Icebridge to fill in more and more gaps.
Fantastic. Are there any further questions for Andy? Just okay. If there are no further questions or comments, it's comes on to me to say a huge thank you to Andy for the seminar tonight. We had really good attendance. Yeah, really thank you very much indeed. And to say to everyone from today, we're actually taking a few weeks off over Easter, and the next seminar will be on the 27th of April, and it will be given by 3 early career researchers who are working on Thwaites Glacier from different perspectives. So I'll put something on to CryoList and so on to remind everyone there's no seminar next week, but we're next back on 27th of April. So look forward to seeing everyone then. So thanks again, Andy, and thank you to everyone for coming.
Thank you for hosting, Tammy.